Good afternoon, and thank you for being here. So today I'll be presenting our insights and results from our investigation of low-level hardware bugs. This is joint work between Technical University of Darmstadt and our collaborators at Texas A&M University and Intel. In actively pursuing the holy grail of trusted computing and its promises for security for our vulnerable software, many solutions and architectures have been continuously proposed in the landscape over the years. Some of these are on the list here. This is, of course, not an exhaustive list. It started with dedicated security chips such as TPMs, and now we have the more popular trusted or isolated execution environments. We have dedicated hardware extensions for runtime enforcement and the attestation of software while it's executing. We have dedicated trust anchors and trusted execution environments for embedded systems. We even have capability-based systems and processors with ORAM constructions in them. Some of these solutions come from academia. That's the big, oops. Yep. Some solutions are proposed from academia. That's the big green whale there. Some are from industry, such as Intel, SGX, and ARM Trustzone. And we also have an emerging open source architecture, RISC-V, that is recently enabling a lot more work in this space and changing the game for system security by setting us free from proprietary architectures and closed source legacy hardware. But anyway, regardless where the solution is coming from, all of these solutions suffer from, they all have one problem, and that is the fundamental trust assumptions of these solutions. The traditional threat model was always a software-only adversary and software-only vulnerabilities. And the focus was on software that executes on top of a processor architecture. It took us a while to realize that there's actually a more complicated microarchitecture underneath all of this and a hardware implementation that we were always assuming was trusted and secure. Now, of course, we know otherwise, right? The recent outbreak of attacks such as Spectre and Meltdown, to name a few, are representing a disruptive paradigm shift in the attack space from software vulnerabilities. These cross-layer attacks exploit issues which originate in your microarchitecture and in the hardware of our systems by means of software, which is a major change from our traditional threat model. And these are either patched by software or microcode, because you cannot actually patch the hardware. Even though the issues originate in the hardware, I cannot patch the hardware after the hardware is fabricated. And this compels us to take a step back and start questioning the security of our underlying hardware in general. Take a closer look at the design process of the hardware, the security assurance techniques that are being used, especially when I am assuming that my hardware is the root of trust of my systems. So we need to actually take a better look into that. And so in our work and in this talk, we go one level beneath the microarchitectural design decisions, and we take a deeper look in hardware implementation itself, and how the hardware is designed, and what are the techniques that are used to verify the security of the hardware implementations before the hardware is actually fabricated. And so how is hardware designed? Hardware is typically implemented by being described at a register transfer level using a hardware description language such as Verilog and VHDL. At least these are the most popular ones. And then this description that models how the data signals flow through registers at clock cycles, then is usually that's thousands of RTL code lines, which are then synthesized into registers, wired, and other logic, and then lay out and then fabricated into the chip that you actually hold in your hand. And now the question is, how do I know this RTL description is secure? What are the techniques that are being used? So in concurrence to the there is a conventional hardware development lifecycle in place for years, and in current to that, there is a security development lifecycle that is being adapted by semiconductor companies recently. The hardware design lifecycle traditionally begins at the architecture specifications through the microarchitecture and then the actual RTL implementation using hardware description language. And then functional verification until the chip is signed off for tape out and fabrication. So security relevant issues would be introduced or bugs would be unintentionally introduced at either the architecture stage or the microarchitecture or at the RTL implementation. But at the microarchitecture stage, most of these decisions have to do with microarchitectural design decisions or flaws in the design decisions, as for example, whether to do cache isolation or not. But at the RTL implementation, the bugs are mostly about how you implement it in hardware. So if you have cache isolation, do you actually implement it correctly in your hardware or not? And these are the level of bugs or the classes of bugs that we're focused on in this work. And so in concurrence to this hardware development lifecycle, there's a security development lifecycle in place, which starts by setting out the security specifications that I want out of my product, the threat model, the assets that I want to protect in my SoC, the adversarial capabilities, everything that I want out of my chip. And then security testing is done or verification to check that the product meets these security specifications. And in order to do that, there is a spectrum of different techniques that are deployed by industry, such as manual code inspection, simulation-based techniques, and formal verification. So the entire process in general is challenging on multiple fronts, but most interesting to us was the spectrum of techniques used and their effectiveness in detecting these bugs before I actually manufacture the chip. So there's a spectrum of different approaches for pre-silicon verification. There's proof-carrying code, where you basically translate or model your system mathematically and the properties that you want, and prove the properties for that system, and give out code that carries the proof. These are not very scalable, and they're a lot more complex to use. There's also a class of approaches that are based on model checking. And again, there are scalability issues with these, but using bounded model checking or constrained state spaces helps alleviate the problem. Most of the industry standard tools out there for functional verification for hardware rely on some form of model checking. There's also a class of approaches that relies on information flow analysis, where you check that you do not have unauthorized information flows from your source to your destination signals. And this is done at different levels of abstraction. And there's little support out there for verifying the hardware with the firmware running on top of the hardware, although there is work underway at Intel and a smaller company, Tortuga Logic, where they try to approach this problem. But scalability also remains an issue. So just like I mentioned, there are fundamental limitations with these techniques. Most importantly is the cross-modular complexity of your SoC designs. Most of these techniques fail to scale with much larger system-on-chips, real-world system-on-chip designs, especially when you need to detect or verify properties that span many large modules of hardware. These techniques cannot capture non-register state, so what happens with your caches. It's mostly focused on register states or the architecture of your designs. They also cannot capture timing flow, so they're focused on functional information flows from one signal to the other, but capturing timing channels is not directly supported in these techniques. Hardware-software interactions are also completely missing in these tools. They either verify hardware alone or software alone. And they're not actually very automated. So you need to anticipate the security properties you want to test for, you need to express them, you need to give them to the tools, and then there's a lot of human intervention involved in the process. Okay. And so knowing all of this, we wanted to test the effectiveness of these techniques, and so we co-organized on real-world hardware bugs. So we wanted to actually have real-world hardware bugs where we try to detect them, and we co-organized with our collaborators at Texas A&M University and Intel the first international hardware security competition, Hackadac, which was co-located with the Systems and Hardware Design Conference, DAC, both in 2018 and in 2019, but in this talk I'll be focusing on our findings from 2018. So we took a deep dive into the bugs that get committed at the hardware implementation level, which is a non-trivial task because real-world hardware bugs happen to be in real-world hardware, which is closed source and proprietary. And so we decided to go for RISC-V SoC, RISC-V system on chips testbed, where we constructed and injected these bugs in close collaboration with our collaborators at Intel, who are hardware security professionals. And we injected these into the SoCs, and we put them out for the teams to try and see how many of these bugs could these teams detect. In both 2018 and 19, over 100 teams from academia and industry participated in the competition, which was pretty good turnover. And after the 2018, after we did this investigation, we did our own investigation using formal verification techniques. One challenge here was how to systematically construct these bugs for our SoCs such that they're also as real world as possible. And so we based the bug selection and construction on real world CVEs and processor errata that involve software exploitable hardware and firmware bugs. And other bugs were inspired by the insights and experience of our collaborators at Intel with issues that they themselves have encountered internally during the design process during the hardware design process themselves. And we basically did this for RISC-V SoCs and reproduced these bugs and inserted them as well as additional security features to augment to these SoCs. We attempted to achieve as much coverage as possible of security critical modules of our SoCs. We tried to inject the bugs into the interconnects, the cryptographic engines, debug interfaces, and so on. We also tried to achieve coverage of the different effects these vulnerabilities or these bugs would have in terms of denial of service, information leakage, privilege escalation, and such that they're also software exploitable, at least most of them. And in doing that, we managed to construct a test bed of over 30 representative RTL bugs in hardware in a RISC-V SoC. So you can check the full list in our paper. And also, please check our repository since we've just open sourced our test bed. So I just want to quickly dive into this SoC and showcase one or two examples of the bugs we've put in there. So this is the RISC-V SoC that we've used for the bug construction. So as you can see, it's not a toy example. It's a real-world design. It's a fully-fledged SoC with an AXI interconnect, a peripheral bus, lots of other peripherals, and a DMA engine, and so on. And we try to inject our bugs throughout different security-critical components to span as much as possible of the SoC. Yeah. And one example for these bugs was a memory access violation bug where there was a slight misconfiguration in the memory, about the configuration of the memory addresses that an SPI peripheral or a serial processor peripheral and the SoC controller module map to. And this is a very simple RTL bug, but it has actually very critical privilege escalation consequences from a security standpoint. And although it's actually pretty minor, it's very difficult to detect that kind of bug using formal verification techniques because it would require verifying very complex bus protocols and their implementation, which spanned many modules of hardware implementation. That kind of bug is actually easier to detect, or was easier to detect by the teams by manual inspection, because the teams sort of had an intuition of what are the high risk areas or the areas where we would inject bugs, and they chose where to focus on. Another example of a bug that was actually software exploitable, it was a bug that was in the finite state machine of the AXI bus address decoder. The bug basically, the finite state machine has to keep state in the sense that it keeps track of every memory access that's coming in and whether it's allowed or not. And it was a small bug in the finite state machine that basically meant if a faulty transaction comes in, a subsequent transaction that is not, if it's also faulty, it still slips through the check. It should check every time whether a transaction is allowed or not, but this bug basically lets one faulty transaction gets in, and then a subsequent one to also slip through unconditionally. And so we show how we could exploit a simple bug like that with the software attack, where we could trigger malicious memory accesses and do privilege escalation. But due to time constraints, you will have to check out the attack in the paper. So one example of a native, okay, Yep. And another example, so the competition itself was, okay. There was also, the teams could also detect bugs that we did not inject ourselves, but already existed in the open source implementations, such as with the real-time. This was an example of a bug, but I won't go through that. Like I said, we had one competition hackattack for the teams to detect these bugs, which consisted of phase 1 and a phase 2. And the teams used different types of techniques, mostly manual inspection, and also dynamic verification, simulation-based techniques, as well as formal verification. However, most of the teams eventually relied on manual inspection because it was the most intuitive and accessible to them. Some teams did use formal verification, but they complained that the tools would not scale well. In our study, we focused on formal verification techniques. We used two of Cadence Jasper Gold's techniques, formal property verification and security path verification. And the two main challenges that we encountered when using these tools, which were formal verification tools dedicated for security analysis, was state explosion and identifying and expressing the security properties that you actually want to detect. So I won't go through our detection results in detail, but I just want you to know that out of 31 bugs we investigated, we could actually only detect 15 using formal verification techniques, and we could only formulate security properties for only 17 of them. And through our findings, basically, we see that there are certain classes of bugs that are fundamentally very challenging to detect using state-of-the-art formal verification techniques. Because they cannot capture timing channels, because they require verification of the software and the firmware and the hardware together. There are bugs that span multiple modules and bugs for which security properties cannot be expressed for. And so what we need now is basically, this is a call for action. We need to investigate and research more scalable hardware assurance techniques and exploit open source hardware to actually do that better, the risks and the gains. And our ongoing work now is to try and have future editions of Hackattack expanding to systems design, system security conferences, and developing hybrid hardware security assurance approaches, which basically combine fuzzing with formal verification techniques to try and achieve better scalability with larger system-on-chip designs. That would be it. Thank you very much.
Questions?
Hi, this is Raju I'm a security researcher at Intel, and thanks for a very nice presentation on the pre-silicon.
I can't hear you. Sorry.
Hi, thanks for a nice presentation. I am from Intel too. So one general question on the pre-silicon security evaluation work you have done. Had you considered any assessment of the impact of the process technology underneath on the hardware? The manufacturing process, like 14 nanometer or 10 nanometer?
I see your point. Thank you. So no, in this study, we focused on logical implementation bugs at the RTL level. I understand that you're referring to physical effects that might come up or physical faults that occur due to the manufacturing technology. This would actually be an interesting thing to explore for another Hackattack. But yes, in this one, we focus on on logical bugs in the RTL implementation per se. Thank you.
Hi, John Criswell, University of Rochester. Nice work. One question I have is your call to action calls for more verification that bugs have not entered into the system, if I understand correctly, right? So formal verification, that sort of thing. I'm wondering if the hardware community is also considering correct by construction techniques. So in the software world, for example, we have type-safe programming languages with type systems that prevent us from creating buggy software to begin with, at least for certain classes of bugs. So are there similar considerations being taken by the hardware community?
Yes, there's a hidden slide on that. So there is work going on in proposing hardware description languages, new ones and extending existing ones where there is security typing of some sort, where you would then identify, okay, these are my signals, this is the security label of each one of my signals, and this is what I expect out of each one of them. The problem is this is like asking software programmers programmers to use Rust and to change their mindset. Most hardware designers don't want to migrate to newer hardware description languages. It also affects your IP reuse. The community is based on reusing IP cores or that's already designed. You would need to migrate everything to newer description languages. But yes, there is ongoing work in that direction.
Okay, thank you.
Thanks.
Okay, let's thank the speaker again.